Welcome back. In Part 4, we learned how topography and local effects shape wind near the ground. Now, we're wrapping up the lower winds series with a deeper dive into how pilots manage these winds in real-world operations using tools, charts, and live decision-making. Let's begin with winds shear awareness. Surface-level wind shear is a major threat during takeoff and landing. Even small wind changes can create big impacts at low altitude, especially if you're close to stall speed or in a critical phase of flight. To stay safe, combine data from METARs, ATPL, and pilot reports. Look for clues like gusts, calm winds with changing direction, or rapid drops in reported visibility. All these can signal possible shear zones developing near the field. Some modern aircraft feature predictive wind shear systems, using radar to detect microbursts or abrupt wind shifts. If you get a warning, go around or hold position, no questions asked. The system knows before you can feel it. Even without high-tech systems, pilots can use windsock behavior, cloud patterns, and experience to anticipate unstable conditions. A swirling windsock or wind split between runway ends is often the first visible warning. Let's now shift to tower and ATC coordination. If the wind is shifting or gusting, ask the controller for updates. They might have multiple winds reported, tower winds, sensor winds, or visual observations, all valid and useful. Request a different runway if you need better alignment. Many airports offer multiple options, especially for VFR aircraft. Don't hesitate to delay your approach or return to holding if the wind becomes unsafe. Speaking of options, alternate airports matter more than ever when winds are unstable. Choose alternates with runways aligned to prevailing conditions, and keep fuel reserves high enough to reach them comfortably if things change. Now let's review low-level wind charts. Products like surface analysis charts and low-level prog charts help pilots visualize pressure gradients, isobars, and frontal systems that drive surface winds. Use them to anticipate wind shifts over time and space. Combine these charts with TAFs, METARs, and GAIRMETS to form a complete picture. For example, if a surface chart shows tightening isobars and a TAF shows increasing gusts, you know conditions will worsen. Let's apply this to a real case, URI departing from a high elevation field with nearby ridgelines. The forecast calls for strong westerly winds increasing through the day. Expect turbulence, shear, and possible mountain wave activity on climb-out. Plan an early rotation, increase your margin on takeoff roll, and stay alert for wind shifts near the surface. Once airborne, climb quickly through the turbulent layer into smoother air. Or picture this, URI approaching a coastal airport in late afternoon. The sea breeze has just arrived, shifting winds from 90 degrees to 140 degrees, creating a crosswind on your planned runway. You may need to request a different runway or increase crosswind correction. Let's talk about winds aloft transitioning to surface winds. As you descend through layers of atmosphere, winds change in speed and direction due to friction. Monitor trend lines on descent and adjust your heading accordingly. On approach, your GPS ground track and heading might not match. That's a sign of crosswind. Adjust your technique using crab or sideslip methods as needed, depending on your aircraft and experience. Also, airspeed indicators may fluctuate in gusty conditions. Don't chase the needle, keep a stable pitch and power setting. Add a few knots above ref in gusty winds to improve control margin. In training flights, these winds are a great opportunity to teach situational awareness. Encourage students to verbalize wind corrections, review wind reports, and anticipate how the aircraft will react before it does. Now let's talk about local knowledge. Some airports are known for tricky winds, whether from terrain, heating, or urban layout. Talk to local instructors, review airfield briefs, and consult with dispatch when planning a flight to a new location. For example, Gibraltar often has strong gusts from the rock. Innsbruck sees frequent valley wind shear. San Diego experiences late afternoon sea breezes. These aren't random, they follow repeatable local patterns. Another key point: braking action reports. Strong winds can dry runways quickly, but crosswinds with wet or icy conditions reduce braking dramatically. If braking action is poor, consider delaying or diverting. During rollout, keep crosswind controls in all the way. As speed drops, control surfaces lose effectiveness, and weathercarking increases. Many crosswind incidents happen on the ground, not in the air. Wind is also a factor in go-around decisions. If the approach is unstable, wind is shifting, or airspeed is fluctuating, go around early. Don't wait for the wheels to touch before deciding. Let's recap techniques for handling surface winds. Use full aileron into wind on takeoff. Maintain centerline with rudder. Transition from crab to sideslip on landing. Stay flexible with speed, spacing, and runway selection. Plan for go-arounds, diversions, and alternates when winds are changing. One last note: winds impact drone operations and helicopters too. Low-level winds shift quickly and vary over short distances. Always conduct site surveys and abort if winds exceed your operating limits. Let's finish with a big-picture summary. Lower winds are influenced by pressure, friction, terrain, and time of day. Gusts, shifts, and shear demand continuous observation and flexibility. Use forecasts, local cues, and real-time tools together. Every phase of flight benefits from wind awareness and adaptability. In the next episode, we climb higher into the sky, exploring upper winds and jet streams. We'll look at how they form, how they affect fuel planning and routing, and why they matter so much in high-level flight operations. See you in Meteorology number 25, Upper Winds, Part 1.